Good morning. I am Costa from NetData. How many use NetData in here? Oh, a few, OK. How many use other observability solutions? Prometheus, Grafana? Nice. Commercial ones, Datadog? OK. And about logs? How many use Loki? OK. Elastic? OK. And the commercial, I understand you are using the commercial one. OK, guys. So I'm going to talk about Systemd Journal. So before I start with Systemd Journal, I want to understand the concept, how I came in touch with this thing. So this is about NetData. NetData is a monitoring system and observability solution that was built out of an accident, let's say. I was pissed off with monitoring solutions that existed a few years back. I had some very difficult problems to solve. No one could detect what was happening. I got pissed off. So instead of going to the gym, I started writing code. So NetData is, let's say that I created NetData to let you feel the pulse of the infrastructure. It works like a beat. So everything is very, in a beat, per second, everything. I tried to solve three problems. One is the fidelity. So everything should be high resolution. The second is the skills that are required to run a monitoring solution. I try to minimize them. And the third is the cost. I try to make a monitoring solution very efficient. So NetData is an open source thing. You can download it and use it and install it. When you install it, every installation of NetData is this pipeline. So it detects metrics, collects metrics, stores metrics, learns from metrics, creates machine learning models, checks metrics with alerts, queries metrics, visualizes metrics, even streams metrics to other NetData or even to third-party databases. So it's an open thing. Now, this pipeline, imagine this, you install it, and you have that thing on all your servers. Hundreds, thousands, it's the same thing. Now, if you install it on an empty VM to understand the difference compared to other monitoring solutions, this is what you are going to get. You are going to get about 300 dashboard charts out of the box. You didn't do anything. More than 2,000 metrics. It's an empty VM. There is no application in there. We are talking about system and components and this kind of stuff. You are going to have 50 alerts. You are going to have a Systemd Logs Explorer, a network explorer, so you can see all the sockets coming in and going out. You are going to have unsupervised anomaly detection for all metrics, 2 years of retention with 3 GB of storage, and it's going to use 1% CPU of a single core. You understand the difference, For the guys that even when you have an agent that is just passing through the data, this is a lot more powerful with just a fraction of the resources others require. So the problem is that when you install it on many servers, you have many dashboards, many alerting mechanisms. Come on, You have to remember the URLs of all servers, the IPs, etc. So what we do is this. You connect everything to NetData Cloud. You access everything via NetData Cloud. Now, you can have centralization points within your infrastructure. So S6 there is a parent. All the other servers push metrics to it. This does all the work. NetData requires this only for ephemerality, so only for operational needs, if you want it. NetData does not require this. And of course, you can have a hybrid cloud where it's more complex and you have parents and many levels, etc. Now, we stress tested this against Prometheus. We installed both of them per second, with 2.7 million metrics, 40,000 containers, 500 servers. And this is what we got. So 35% less CPU, half the memory, less bandwidth, almost no disk I/O compared to Prometheus, And we have an amazing half a byte per sample on disk. Half a byte. Prometheus has 2 point something. Now, and the University of Amsterdam this December published a study that they found that the data is the most energy efficient agent and it doesn't have any impact on the monitored applications, which is great. In terms of love, the data has 1 million downloads a day, every day. The community grows with about 5,000 new users a day, something like this. So it's a popular project, and it leads the observability category in CNCF. Now you understand that all this was an intro just to understand the concept. We have a monitoring solution that is distributed, it's decentralized. The data are all over the place. You don't have a database. Why we did it like that? Because that's the only way to have high fidelity insights without the problems of scalability. If you have Prometheus, then you have, and the infrastructure grows, you have to go to Thanos, and it becomes complicated. And if for commercial providers, it becomes expensive. We all know how expensive Datadog, for example, is. So the idea is that when you have a centralization point, then you have to cherry pick metrics, you have to lower the resolution. But if you leave everything out there, if you don't move the data, then you have the opportunity to have high fidelity monitoring. You can ingest, you don't care about cardinality, you don't care about granularity. Let them all be in. Now, how do you solve this for logs? What do? We started building our own logs management solution. And after a year or so about last year this time, I realized what systemd journal is. And I said, wait a moment. This thing is heavily underestimated. We have not understood what it is. So let me give you a brief. For systemd journal, a log entry is a series of fields, key value pairs. Every log entry can have its own, every log entry. So one log entry has these fields, the other log entry, the next log entry has some other fields. Systemd journal is the only solution that can actually ingest an infinite cardinality of fields and values. It doesn't care. And all of them are indexed. Each field, each value, all of them are indexed. It's easy. You can query it like this. So you can do journal.ctl fields to get all the fields. You can get journal.ctl field equals this value. Field equals the field name, the field key, to get all the values. And then you can query the logs for a specific field and a specific value or a combination of them. That's easy. There's a command line tool. It has persistent storage and volatile storage. So logs can be committed to disk or logs can be committed to RAM. And this is actually how it works at boot. When the system boots, systemd journal commits to TMPFS until it mounts everything and then moves the logs to persistent storage. The same will happen if, for example, a disk vanishes. A disk is full. A disk is detached from the system. It's lost. It's a network drive and cannot access it anymore. Logs are not lost. Logs go to TMPFS. And, of course, mainly because it's configured to use as much available storage as possible, it automatically rotates logs and does all the magic required in order for the logs to be not to be a problem for the operation. Now, the data availability, this thing has been designed for amazing data availability. So it's an append-only format. It writes to files. It's a journal file, it's a file, like a log file. It's binary, not text. But it's append-only, so it's the same as text log files. it has inside it chain splitting. This chain splitting allows it to recover as much as possible in case of corruption. So you have a corruption on disk. Journal, systemd journal will recover as much as possible. You're not going to lose this chain or that chain where the corruption was, but you will not lose everything. It has checksums for integrity, so when you query that thing, everything is validated. You are sure that you get the right log entries back. And the most amazing thing for security is that this has this FSS, forward secure sealing. What this does is that every chain is signed. So if you tamper the files, it will detect it. And it will tell you, you know what? This has been tampered. Now, systemd journal needs a server only for ingestion. Only for ingestion. So to query, you don't need a server. You have a library that you use in your code. It's a simple call. You say, I want to query from here to there. And this opens the files. So the files are designed to be memory mapped. And the good thing with this is that the first is that it has high concurrency. It utilizes the caches of the system. But it also provides the ability to transparently query any files that are there without limits. So if you have, let me go to the next slide because I think you are going to understand it better. So this is how you build centralization points. You run on the edge systemd journal upload. You run on a centralization point, systemd journal remote. What does it happen? The upload part streams the logs in real time to the centralization point, which creates journal files. So every, I don't know, 5, 10, 20, 100 megabytes, and depending on the configuration, it will generate a new journal file. Now, when you query, to go back to the previous slide, you actually open as many files as there are on the disk. And you query them all in parallel. So the moment that libsystemd opens the files, they become one stream, all of them, across all servers, if you have multiple. This made it amazing, extremely flexible. So it's a universal logging, of course. So it can receive messages from syslog, from kernel, from audit, from dbus. Sorry, my Reddit. From units, the standard input-output of the systemd services, and there is a native journal protocol that looks like the beginning, key-value pairs. They separate it with an empty line. Key-value pairs, you continue, an empty line, you split the message, and go on. Now, a comparison, in order for, since you use Loki and Elastic and the likes, a comparison for you to understand. Loki organizes logs into streams. Every stream has constant fields. They cannot change. So it's a set number of fields with the values fixed for a stream of logs. Okay? And the key thing that you have there is a time series. When you query that thing, you understand that this is not indexed. Whatever is in the stream is not indexed. The problem is that the problem needs to be solved at the front end. So the front end receives raw unprocessed logs, and it has to process them and do whatever in order to understand. To give you the time series at above of how many logs you have and the likes, they have a mechanism that is similar to a metric in Prometheus, where they store the trend, how the logs progress over time. Search capabilities, not that many, mainly because everything needs to happen at the front end. So within a stream, just limit the time to make the front end faster, and query by giving expressions or whatever at the front end that only the front end can execute. Elastic. Elastic is on the other far end, extreme indexing of everything. So it splits for every field, every word, and it has a reverse index. And of course, this makes it very powerful, but at the same time, complex, heavy, and with extreme footprint. So you need storage for that. Loki, what I didn't say is that the disk footprint of Loki is similar to compressed text files. It's very close. So the same size that you are going to get if you have a text file and you zip it, the same size Loki database will have. Systemd journal is somewhere in the middle. So it indexes all the fields and all the values. It doesn't go into the word level like Elastic does. So if you have in one key, in one field, 10 words, the systemd journal will index the whole of it, all, the entire phrase, while Elastic will index every word. Extremely fast ingestion, so it doesn't care. If you try, for example, to recreate what systemd journal does with Loki, Loki needs an unimaginable amount of memory. So the cardinality explodes for Loki, and the way that it has been designed, it actually cannot do it. You give it gigabytes and gigabytes of RAM, and it cannot do it. But for systemd journal, this is the beauty. It's that it indexes everything, and at the same time, it's fast. It doesn't need any memory. It's extremely lightweight, just a few megabytes of memory, 5, 10 megabytes of memory, something like that. Almost wire speed, so how fast is your network, how fast is your disk, systemd journal ingestion will do it. The key weakness with systemd journal is that there is no rewriting rules. In all the other solutions, you have a mechanism there to actually process fields, rename them, rewrite them. In systemd journal, there is no such, at least from systemd, because we created one. So how did we improve it? What Nedata did? So when I realized this, guys, it was, this is unbelievable that they have done a database like this, because it's a database. So this thing has totally dynamic fields, every log entry. Imagine it, you have log entries from one application, from another application, even from the same application. The fields can change dynamically per row, per log event. This is very dynamic. Imagine your application being able to log, to dump the exact queries that you received, the exact memory state of the internal processes that you are doing or whatever, a full backtrace of everything you have. It even accepts binary data. So if you want to attach some binary data to a log, OK, let's do it. It cannot open it, but it will query, give it back to you, etc. So the idea is that, at least for me, it was, what? That's amazingly good. It's a hell of a database inside systemd. The bad thing is that they didn't make it a library. So you have as a library the read, you cannot have the write. The write is inside their code. It's open source, of course. So since you have this, and you have all the mechanisms to replicate that thing, so to push them around in your infrastructure, you have the mechanism to query that files, dump everything in text or whatever you want, because journalctl can do all this. It's an open project, so you have it already. Even if you don't know it, guys, this exists in your systems. This is how your systems boot, unless you have Slackware or something and you don't use systemd. But for most, Debian, Ubuntu, CentOS, all of them, Fedora, Red Hat, all operating SUSE, all operating systems today rely on systemd. And this thing is inside our systems, all of them. It's funny, when I realized that, I said, wait a moment, the guys have this amazing, the world has this amazing database inside all our systems, and we decide to move the data to another. Why? What's the reason? It's amazing the way it is there. So I try to understand what's happening there, and how we can improve that thing. So the first thing is that we realized that queries were slow. But this was not by design. It was implementation of glitches. So we did the same work we do with Nedata, and we analyzed the performance of journal CTL. And we found little fixes. It was easy, little fixes, but they improved performance 14 times. So we submitted patches to systemd. We pinpoint the problem to them with patches, with code, for them to fix it. The good thing is that in our viewer, the dashboard that we have for systemd journals, we managed to bypass the performance problem, even on old. So we patch libsystemd when we load it for us. We don't change the system. But this plugin uses an improved version of systemd that we improved it at runtime. Then we created this tool. This tool is the equivalent of what Loki prompt tail. Prompt tail tails logs, filters, manipulates some fields, and pushes everything to Loki, right? So we did something similar for log2journal. So log2journal can extract fields from sources. If it is JSON or log format, it does automatically. You don't need to do anything. If it is a plain text file, whatever, unstructured, structured, doesn't matter, you have regular expressions where you can extract the fields that you are interested. Once fields are extracted, we go through a rewriting process, filtering, and then we output everything to systemd journal. This makes it possible, for example, to put your nginx logs or your HAProxy logs into systemd journal with everything structured. Every item in there, a field, and properly indexed by systemd journal. We created that. What is important here is that log2journal does not need Linux. It runs anywhere. It's pure C code, no external dependencies except from PCRE patterns. So it can run on anything, even on Windows. And another tool, there is a tool already that's called systemd cat. Do you know that? It just pushes an entry to the systemd log. The problem with this entry is that it's not structured, so you can only give a message to it. We created systemd cat native, which takes as input the key value pairs that systemd journal requires. So systemd cat native gets a stream of key value pairs where log entries are separated by new lines, an empty line, and then it can push this stream to a local systemd journal or to a remote. So on FreeBSD, for example, you can have log2journal and systemd cat native streaming data to a central Linux log server that runs systemd. Now, the pipeline that we achieved looks like this. So you have the local sources. It's very distributed. It's very similar to what we have in Nedata. The first pipeline I showed you about the metrics in Nedata, this is very similar. So you have some local sources. Either they go directly to journald or they go to text files. If they go to text files, you have to use log2journal to actually push them to systemd journal. Systemd journal stores them in journal files. And then we have Nedata that queries and visualizes that thing. And if you want, you can push them to another server. So you can build centralization points. Now, this allowed us to have, the same philosophy of decentralization. Keep your data as close to the edge as possible so that you don't have scalability problems. And Nedata will figure it out. And if you want to build centralization points for operational needs, do it, but it's not required. Installing Nedata on all these points will just pick up also system journal logs. So I have just a couple of slides for this. The first thing is that systemd journal has some interesting fields. There are a lot more. I just cherry-picked 3. Boot ID. Boot ID is a hash, a UUID, that changes on every system boot. It's on every log line. Every log line has the same boot ID. So you can easily say, hey, what happened on the system during that boot? You find its UUID. There is a query to find the UUIDs by time, etc. And you say, what happened there? And you get all the logs of a specific boot of the VM or the computer. The next, the systemd invocation ID is about systemd services. Oh, I'm done. OK, finished. 4 minutes, OK. Invocation ID. Every time your application starts, a new ID is there. So you can easily query that session of your application. And message ID is what shocked me when I realized it. So there are fixed hashes, a fixed UUID. It's a random, but it's fixed. That if you query that thing, you get the GORTAMs, you get the crashes, you get, I don't know, unit status, you get system status, shutdown commands that were run, and a lot more. So what we did in the data, it's a user interface that looks like Kibana or Grafana for Loki. It's very similar. It has a time series. It has a table with the data and a ton of filters on the right. So it's the same experience. The difference here is the following. This is why I have this screenshot there. If you check next to the title, it says it has 15 million entries there. 15 million log entries in that time frame. The blue one are estimated. You see, it's the estimated on the middle. It's the blue one, the big one. Now, look what sampling we did. In order, the all monitoring solution, even Loki, Grafana Loki, even Kibana Elastic, they just go to the end, last 5,000 entries. When you have a lot, they go to the last 5,000 and they sample there. We sample at least 1 million. We start sampling at 1 million. Up to 1 million, it's raw processing because it's fast. Okay? And when you have the crazy setup, hybrid setup, we have built inside NetData, with methodologies of NetData, all the routing required for you to go to a grandparent or NetData Cloud or somewhere and say, hey, I want this plugin there to run systemd journal and give me the data. Okay? So you can query live data from your entire network. I will not talk about this. This is about NetData and what we do because this is open source. Everything that I show you is open source, guys. We have a SaaS offering. This is what we sell on top of it. Thank you very much. On time.
Perfect timing. Thank you, Costa. And we even have time for 1 or 2 questions if there are any. Any questions for Costa? There's one over there, so I'm going to throw it a little bit.
Hi.
Hi.
A very interesting topic. Thank you. My question was about, you said you are keeping the data at the nodes level, so what happens when you cycle a host?
As I said, do you remember that I showed you a thing that was called centralization? This thing exists for both metrics and for logs. So when you have ephemeral nodes, like a Kubernetes cluster or whatever, then you have to think how to offload the data, the observability data, from that node to somewhere else. But the idea is that you keep them somewhere next to it. You don't need one big across your infrastructure. You may have 2 sets, 2 islands, let's say, of ephemeral nodes. You just put a parent there. You have the data, a replica there. You get it? Yeah. So the data allows you to replicate data. And you can have a replication factor in all this. How many replicas do I have of my data? And every replica can have different retention settings, etc. So you can control how much disk space you want to dedicate to everything. So when we query stuff, we know that there are multiple copies of the data, and we use the right one all the time. Okay?
Thank
But
you.
this is multiple independent centralization points. As many as you want. The more, the better. You don't need one. Other question? Or we're done?
One last question, if any. Otherwise, thank you very much, Costa. And we...
Thank you very much, guys.
Thank you.